Let's start with the next talk. So it's a real pleasure to have Mark Zhandry here. He's going to be giving he's going to be speaking about his breakthrough result with Takashi and on quantum advantage without structure. He'll also be here tomorrow speaking about at the intersection of quantum and crypto. So you'll have plenty of time to interact with him both right after the talk and tomorrow. Mark, looking forward to it.
All right, thank you. All right, so yes, I'll be talking about my recent paper. Here's the title: Verifiable Quantum Advantage Without Structure. So let's just see what all these terms mean. So this one's pretty simple. For a quantum advantage, we just mean we're looking for a problem that can be solved in quantum polynomial time, but take super polynomial time classically. This one, the other term is verifiable. So we want the advantage to be verified. And what we mean by this, think NP. We want it to be that the problem, if you solve it, that you can efficiently verify that you solve it. It's potentially even more interesting or more broad than NP. You can imagine interactive protocols, protocols with a quantum verifier, but just think NP for simplicity. And then the last question, and this is the squishier one, is what kind of structure do we need for quantum advantage? And this isn't really a well-defined notion, and there's certainly many reasonable ways to talk about structure. In this talk, I'll take a cryptographic view of structure, and really the heart of it is that with the current state of complexity theory, there's no hope of actually proving unconditionally a classical lower bound that would demonstrate quantum advantage. And so all of our lower bounds for classical algorithms are going to have to rely on something additional, whether that's an oracle or a computational assumption. So I'll be thinking about two different notions of structure. So one is, okay, so we can't get an unconditional result in the real world. So what we're going to do is we're going to pretend that there's a black box in the sky that has a function f inside, and classical and quantum algorithms can query this function. Right? And what we want here is for this function f, so it's certainly an idealized world where we're imagining that there's this black box, but we want it to be as close to the real world as possible. And the most natural thing to think of here potentially is that this function f is a uniformly random function. Now, uniformly random functions certainly don't exist in the real world, but we can heuristically approximate them with standard cryptographic tools. The other type of structure we'll be thinking about is a conditional separation. So here, there's no oracles. We're going to be in the standard model, real world. But we're going to need to make computational assumptions in order to justify the classical hardness of our problem. And thinking of typical assumptions we make in cryptography, we can roughly, okay, it's not a line. Many of these are incomparable, but we can think about different assumptions. And really, what we're going to care about for structure, what we're going to define as structure, is that it doesn't imply public key crypto. And we'll see why I take that as the threshold in a moment. So what we want is that we can base quantum advantage on some assumption, some computational assumption, whose if it's true, it doesn't necessarily imply public key crypto. Maybe it implies symmetric key crypto. And the reason basically for this is that in order to get public key crypto, all the constructions we have tend to have a lot of structure to them. Again, structure being informally defined. So, factoring, discrete log, pairings, they all have a lot of algebraic structure that ends up getting exploited by the quantum algorithm to prove easiness. LWE, we believe, is even quantumly hard, but it still has a lot of structure that it lends it to things like fully homomorphic encryption and so forth. And this notion of structure, sort of drawing the line between symmetric and public key crypto, also naturally corresponds to our notion of structure in the oracle setting, because we know that a from random oracles, we can get all of symmetric key cryptography more or less. And yet, on the other hand, it's widely believed that from a random oracle, it's insufficient to get public key encryption. And this is the famous Impagliazzo-rooted impossibility result. Question?
This is just very, this question is just down in the weeds. I'm sorry about that, but I just wanted to know anyway. On your chart, you're taking symmetric crypto as a synonym for private key.
Yes.
And it's my impression that it doesn't quite 100% always mean that. It can mean that both parties do the same thing, which and that is possible for public key. You just mean it as
Yeah. So I'm really thinking of symmetric. When I say symmetric key crypto, I just mean private key crypto, but there's no public keys around. Right. All right. So I won't spend too much time on this slide, but we have a lot of sources of quantum advantage. Some of them are verifiable. Some of them have no structure. Some of them aren't anything. But at least according to the definition, the informal definition of structure we use in our paper, there's nothing at the intersection here, and that's what we're going to see today. Okay, so before getting into the results, I just want to say a few more comments. So first, if we want something that doesn't involve oracles, that's just in the real world, all sorts of advantage for problems in NP that we know of rely on period finding. The connection to period finding is often non-trivial, but at the end of the day, that's the quantum algorithm ends up using period finding as a subroutine. And so, it could be based on this. You might wonder, is quantum advantage in NP? Is it sort of inherently tied to period finding, or is there something else? And this one also, maybe this one's less important, but all existing structuralist sources of advantage that we have, things like Fourier sampling and whatnot, are all for sampling problems. So the task is not to find a single solution to a problem, but it's to sample from a distribution that closely approximates some desired distribution. And you can turn sampling problems into verifiable problems, but it's sort of, with the sampling problem, it could be that there's non-zero support on the entire domain. And so they're sort of seem inherently disconnected from efficient verification. And then lastly, I wanted to just address this Aronson and Baynes conjecture, so they stated it in 2009, but say that it was folklore since around 2000 or more or older. And basically, forget the exact details of the conjecture, but it more or less says that if you're looking at query complexity, that if you have an algorithm, a quantum algorithm, A, that makes queries to a random oracle and outputs a bit, that there is a classical algorithm that can simulate the view of A, also making polynomial number of queries. S might be computationally unbounded, and it would have to be if, say, A is factoring integers. But in terms of just the query complexity, S is polynomially bounded. And the implication here, if this conjecture is true, the implication is that random oracles shouldn't help separating BQP from BPP, right? Because for any decision, right, the only way in which you could have assuming the conjecture is true, the only way in which if your quantum algorithm couldn't be simulated efficiently is if S was actually doing something computationally intractable. But that kind of the whole point of moving to an oracle setting is to be able to look at the query complexity. And the conjecture says that looking at the query complexity won't get you anything. Okay, so what are our results? So we show, relative to a random oracle with probability 1, that there is an NP search problem that is in BQP and not in BPP. So in other words, it can be solved efficiently on a quantum computer, but not on a classical probabilistic computer. The reason that this doesn't violate what I just said on the previous slide about the Aronson and Baynes conjecture is that it's a search problem here. And if we go back to the previous slide, our algorithm here is solving a decision problem because it's only outputting a single bit. So we actually don't say anything about the Ernst-Cambanis conjecture, despite seeming to get close. So yeah, there's this NP search problem in BQP, not in BPP. And I guess I should also say that the decision version of this problem is trivially easy. All instances are yes instances, and that's also why we don't contradict the Ernst-Cambanis conjecture. Then we show basically how to embed the search problem into cryptographic objects to get a variety of cryptographic objects that are classically hard, but are quantum easy. And then we also use the problem as pretty simple to turn this problem into a verifiable proof of quantumness. So it allows a quantum computer to prove to a classical verifier that they are in fact running a quantum computer. And prior results were known, but they required LWE, structured assumptions, and they also actually were interactive and lacked public verifiability. And so we get minimal rounds, public verifiability relative to a random oracle. And then lastly, we actually say, well, okay, we don't contradict the AA conjecture, so we're going to, let's just assume that it still holds. And then we actually show that we can lift our verifiable proof of quantumness into a certifiable randomness protocol. So a quantum device can generate a random string for a classical client, along with a proof that it actually was generated randomly, and conditioned on the verifier accepting this, the verifier will actually be convinced that the string was uniform. And that, it's trivially impossible classically, because you could just have the prover run the honest prover protocol, but with no random coins. So we can get this. Again, this was also, certifiable randomness was also known from LWE, but it required more interaction. We get less interaction, but now we're also making this, this AA conjecture. And then lastly, this isn't really a result, but we're just saying that you can heuristically instantiate the random oracle in our constructions with some cryptographic hash like SHA-256, and very plausibly get a non-relativized real-world instantiation of all of these objects with conjectured security. And I guess the point is that the conjectured the security of SHA-256 is believed not to imply public key encryption, so it's pretty low down on the spectrum of the computational assumptions. All right, so let's just dive into the construction. So we're going to start with some sort of linear code. We will see what properties we need of it, but it's going to be high dimensional. So here I drew one that's 2 dimensions, but think 100 dimensions or something like that. We're also going to want a large alphabet. Normally, when you're designing error correcting codes, you want a small alphabet, but we're going to take a large alphabet, and we'll see why that's needed. And we also want it to be linear, so it has this nice lattice-like structure. And I'm going to use the word code just because it sort of makes sense with what we're going to end up needing of this set C. But you can also think of it as like a discrete lattice or something like that. All right, so the first thing we do is we're going to just, I don't know if you can really see, what we're going, yeah, okay, this slides don't turn out so well in here. Yes, so on the screens there, you can see that there's these vertical stripes. So basically what we do is we're going to first look at the x coordinates, and we're just going to randomly select half of them and call them valid, and the other half are invalid. Right, so now solutions to our problem are going to be code words that have a valid x coordinates. How do we choose what are the valid x coordinates? This is where the random oracle is going to come in. Basically, for we're going to think of the random oracle. The domain is our alphabet. The alphabet is a single bit, and whether that bit is 0 or 1 tells you whether the symbol is valid or not. Okay. Now, this didn't create a hard problem by any means. We can randomly sample from the linear code just by linear algebra, and with probability of half, your random code word will have a valid x coordinate. If you fail, you just try again. In expectation, you'll generate 2 random code words before you find a one with a valid x coordinate. So what we're going to do is we're going to utilize the fact that we have a high dimensional code, and we're just going to repeat the process for the y coordinates, the z coordinates, and so forth. So for every coordinate, what we're going to do is we're going to choose a random subset of symbols, and we're going to say that those are valid for that coordinate. And what the problem is to find a code word where all of the coordinates are valid symbols. And that's it. That's the description of our problem. Okay, well, it's not it, but that's the gist of our problem. And now we just need to ask, why should this be classically hard? Why should it be quantumly easy? And in answering these, we'll see what code we actually need to use. Okay, so let's start with classic hardness. And I guess just intuitively, we can think of this problem as sort of an instance of a broader class of problems that have made appearances in crypto, which I'll call domain-constrained linear equations. You basically have, what I'm calling domain-constrained linear equations is the goal is to find a solution to a set of linear equations that also satisfy some additional constraints that are naturally nonlinear. So we can think of the short integer solution problem of ITI as a random linear code combined with a low L2 norm. Random binary linear codes with low Hamming weight, so a different norm here, were considered in a handful of works a few years ago. And in general, like we believe cis is hard. We believe this binary code with low Hamming weight is hard. And so it seems likely that if your second constraint is sort of sufficiently nonlinear, it seems like there's a good chance that you might actually have a hard problem. And in our case, we can actually prove unconditionally that this problem is classically hard using the random oracle. So it's a query complexity lower bound saying that the number of queries you need to make to the random oracle has to be exponential. And maybe I won't spend too much time on exactly why, but the gist is if C satisfies this property of list recoverability, we can actually prove classical hardness. And roughly what list recoverability is a generalization of list decoding, where for every what is list decoding? You have one symbol for every position, and you're trying to find all code words that could match a sufficient fraction of those symbols. List recoverability just generalizes that so that you have a list of symbols in each coordinate. And if you have a list recoverable code, we can prove this is classically intractable. This isn't particularly novel on our part. There was a related construction. Their goal was something completely unrelated, but they also used list recoverability together with random oracles to build a hash function that was hard. Yeah. Yeah.
What is list recoverable and what is hard?
So if the code C is list recoverable, then it is classically hard to find a solution to our problem in the relative to random. So to find a code word where all of the coordinates are valid.
Yeah.
According to
I'm missing a sentence or just a thought. Why is that the right direction?
Good. So right. What is list recoverability? It's for every coordinate you have a list of code words. And you want to be able to find all code words that sort of lie in the appropriate, every symbol lies in the appropriate list, or maybe you can have a few that lie outside the list. And the idea is that these, so if you can find all code words in particular, it means that the set of such code words can't be too large. And you can, the sets of these S's are the sets of symbols for every position. You can think of them as the queries that the classical algorithm makes to the oracle. And so so actually list recoverability sort of trivially gives you a classical hardness lower bound against algorithms that make all their queries in parallel. So if all the queries are in parallel, literally what you say is I look at all the queries for every coordinate, and list recoverability guarantees that there's a sub-x, so it's not quite polynomial, it's sub-exponential, guarantees that there's a sub-exponential number of code words that could be consistent with the queries that the adversary made. And then then it's just a union bound. For every code word that you have, there's a exponentially small probability that it was valid. You have sub-exponential number of code words, and now you get your exponential lower bound.
So you just mean code is in. You haven't said anything about minimum distance or anything.
No.
So you just mean code as in a subset of the.
It's a subset of all possible vectors over the alphabet. And then this is the one property. Well, we'll stipulate another property later. For now, this is the one property that we will require.
Right. So the connection between it being a code and it being sort of good, classically hard. Your problem is that sort of, you could say if you make few queries, then sort of because it's a good code, then there should be no code words that are consistent.
No code words consistent with the queries you made.
Yes, right.
And then anything that's not consistent with
You're
the
just
queries you
guessing
made.
randomly.
Yeah, exactly.
Okay. Yeah, good.
Yeah, so essentially what list recoverability says informally is that the best strategy to attack our problem is to just sample random code words and hope for the best.
Yeah.
Right. So the way the oracle shows up is that it's really, so we're setting the queries to the oracle to be these sets S. Right. So if you didn't have an oracle, you couldn't. It's not well defined to talk about queries making the oracle. So that's kind of the first part where the oracle comes up. Yeah. So in this theorem down here, list recoverable implies, so if I were to write it formally, if the code sees list recoverable, then any Pascal algorithm making the sub-exponential number of queries would have a exponentially small probability of finding a valid code word.
Why is it called least recoverable? It seems like something is not possible to do, and it seems that something should be possible to do according to the definitions.
I mean, it wasn't my term. This is a term from the literature, but the idea is I mean, I don't know why it was called recoverable as opposed to something else, but usually it's a generalization of list decoding, and usually we think of list decoding as something you want to be able to take your set of symbols and find the code words consistent with the symbol. So it's usually an algorithmic problem to do so efficiently. We're turning it on its head and saying we're going to actually use the existence of a efficient pattern. We actually don't even care that's efficient. We just care that the size of the set of possible consistent code words is not too large. But yeah, usually it's a design goal in order to get efficient algorithms that you want something to be list decodable or list recoverable. And we're using it. Okay, so that's classical hardness. I think the more interesting part is quantum easiness. So why should this problem be quantumly easy? And what we're going to do is we're going to use a technique that was used by Regev when he defined the learning with errors problem. And we're going to change it, but this is sort of the origin of the idea. So something that I call multiplying quantum states. And what do I mean by that? I mean that, so I have two input states. So I'm going to be talking abstractly for now. We'll see the connection to our problem in a moment. So here's the general task. I have two input states. Here I have a Dirac comb and a Gaussian. And what I want to do is multiply the states together in the sense that the weight, so the domain here, the x's range over the same values for both of these states. And I want that my output state, just the weights on every x are the product of the weights in the original states. And in general, there's a normalization factor here that is sort of important, but I'm going to largely ignore. But this is the idea. We want to be able to do this. And I guess just so looking ahead, why do we want to do this? Well, basically our problem, as well as these general domain constrained linear equations, there's sort of two easy problems. One is solving the linear system, and then one is finding short vectors or finding vectors with valid x coordinates that may or may not be code words. And what we're going to do is we're going to sort of individually solve the two problems and then use the state multiplication to try to combine the solutions together. Okay, so how might we solve this problem? How might we compute the multiplication of these two states? Well, we're going to do the one thing that I know how to do with signal processing, and that's switch to the Fourier domain. And in the Fourier domain, so now our two states become some other states. And the product state, there's this well-known convolution theorem that says that the product of the two input states, when you switch to the Fourier domain, becomes the convolution of the Fourier domain version of your input states. So we've now changed our problem from computing this product to computing this convolution. And why does that help us? Well, here's why. So here's our blueprint. So we're going to assume that we can construct these two input states separately. Let's just immediately look at them in the Fourier domain. And so we can write the joint system like this. Then what we can do is we can add in superposition. So we can take x and y from our two input states, and we can add them together to get x plus y. And that's what we need for the convolution. Now, the tricky part is that our quantum operations have to be reversible. So we can't just replace x comma y with x plus y. That's not a reversible operation. Given x plus y, information theoretically, you can't figure out what x and y were. So what we'll think of doing is mapping x comma y to x comma y comma x plus y. Or you could have even done just x comma x plus y or something like that. But the point is, you need, in order for this to actually make sense and be physically realizable, you need to keep at least one of x and y around. So then the last step is to somehow get rid of this lingering x or x comma y or whatever, in order to just be left with x plus y at the end. And then if we can get rid of x comma y here, this is exactly the convolution. This is exactly what we're trying to solve. Right, and using the reversibility of quantum computation, going from x comma y comma x plus y to x plus y, it's equivalent to go from x plus y to x comma y comma x plus y. So what we're gonna, even though we're going to be going in the one direction, we can think of it as really we're trying to go from x plus y and actually figure out what x and y are from that. So it becomes a decoding problem, taking x plus y and mapping it to x comma y. Right. Okay. So for now we're just going to assume that we can construct them separately. This is basically trivial, and then this is where kind of all the interesting stuff happens. And it's certainly not even always possible. There's right, like as we said, x plus y in general does not reveal what x and y are uniquely. But we're going to hope that the nature of our problem actually allows us to do this decoding. So just as an example, so Regev's proof was sort of more complicated because he was proving something slightly different. But you can actually view Regev's proof of the hardness of LWE as an application of this. So what does he do? So the one state is the indicator function for a linear code. And the other state is going to be this Gaussian weighted superposition centered around 0. Both of these we can construct without too much difficulty. So if we were to say, measure the first state, we get a random code word. If we were to measure the second state, we'd get a short vector. And then if you compute the product and measure that, the product is going to be short vectors in the code, which is the short integer solution problem. So what Regev said is, okay, we want to solve the short integer solution problem. So let's switch to the Fourier domain. The Fourier transform of the indicator function for a linear code is an indicator for another linear code called the dual code. The Fourier transform of a discrete Gaussian is another Gaussian, or there's some error term, but we can think of it as some other Gaussian. And now what's the convolution? It's the superposition of x plus y's, which is basically random dual code word plus random small error. And this is the LWE problem. So if you could solve the LWE problem, so taking a noisy code word in the dual code and actually figuring out what the code word was, then through Regev's reduction, you would be able to solve cis. Now, Regev was unable to solve the LWE problem and in a sense become, a famous conjectured hard problem in cryptography. And this proof can be sort of turned on its head to give justification for the hardness of LWE, because you can say, well, if I'm confident that cis is hard, then LWE must be hard as well, because if LWE were easy, then you could complete the reduction and solve cis. Right, so that was Regev's work. And now what we're going to do is try to apply this general idea to our construction, to our problem. So we're going to do the same thing for these alpha x. So our first state is going to be the indicator function for this code C, which again we can just construct easily using linear algebra. And then the other state are going to be the indicator function for valid coordinates. So it's basically going to be a superposition over all vectors, not necessarily in the code, but all vectors that have valid coordinates, where all the coordinates are valid. And then the product state is just the intersection of these two, which is exactly what we want. The product state is going to be a superposition over solutions to our problem. They're going to superposition over code words that have all valid coordinates. So what we need to do then, okay, so we're going to try to solve the multiplication problem for these two states. So we need to figure out if we can solve the convolution problem, which then reduces to solving this decoding problem. So what is the decoding problem? So here's the dual code is just going to be some other linear code. And then the more interesting part is going to be the valid coordinates. So if I were to zoom in just say on the x coordinates, right, the indicator function is just a random function, right? It says for every symbol with probability half, it's 1, with probability half, it's 0. So up to normalization anyway. This is what our state looks like for a single coordinate. It's just kind of randomly oscillating back and forth between 0 and 1. And then our overall state for the valid coordinates is just the product of these kinds of states for every possible coordinate. So when we look at something like this in the Fourier domain, it's actually has a pretty nice form. So we're going to have the Fourier coefficient at 0 is going to have this big spike where the magnitude is about 1/2. And that corresponds to the fact that this, the area under the primal signal is about 1/2, right? Because in expectation, every point has its value is 1/2. So we have this huge Fourier spike at 0, and then all of the other Fourier coefficients are basically uniform. There's a complex phase that encodes all the information it needed to sort of reconstruct the oscillation back and forth in the primal domain. But if you just look at the magnitude, you get essentially uniform. So what is x plus y then? Once we move to the Fourier domain, what is x plus y? Well, x is going to be a dual code word, and y is going to be a vector of things distributed like this, right? So basically in every position, we're going to have a 1/2 chance that the vector in that position will be 0, and a 1/2 chance that it'll be uniform in the rest of the domain. Yes.
You just need one dimension here, or?
So this, because I can't draw in multiple dimensions, this is just one coordinate. And then you're going to have the product of many of these for every single coordinate.
Decay exponentially then the norm on 0?
No, because it's a finite domain, right? It's just whatever our symbol space for the code is.
Okay.
Yeah. So I mean, maybe the way I drew it sort of makes it look like it should decay. Otherwise, the area under is exponential or infinite. But no, it's a finite domain. Just whatever the size of our symbol space is. but the crucial point is just that it has this spike at 0 and is essentially uniform everywhere else. And then we repeat that for every single coordinate. Right, so X is a dual code word, and Y, if every single coordinate basically has a probability of a half of being 0 and a probability of half of being random. And so what we get is that our X plus Y is dual code word plus random errors in about half of the coordinates.
So in other words, about a quarter of the bits are flipped.
Well, these, I mean, these aren't bits.
They're not bits.
Yeah.
Or they need not be.
Right, and in general, our symbol space will actually be exponential.
Okay.
Right. So this is actually a well-known problem in coding theory, right? You have a code word, you introduce some errors, and you want to figure out what the original code word is. That's the decoding problem. And this is actually often one of the examples of where list decoding is motivated. Because we're basically, it turns out, going to want to correct for more errors than you can handle with unique decoding. But we can use list decoding and then just use the fact that when we have errors, they're uniformly random to argue that actually there is only a unique code word. So in the worst case, there could be a lot of code words, but with overwhelming probability, there will always be a unique code word for the sort of the parameters we choose.
When you say a lot, would it still be only polynomially many?
Yes. Yeah. So it sort of depends on the exact parameters. So what we're going to want is we're going to choose some, it could be a constant, let's say epsilon, that's pretty small, and we want to be able to decode a half plus epsilon errors. Right, and that basically, right, because so we have errors in around half of the positions, but it could be a little more than a half. But with overwhelming probability, the number of errors won't exceed a half plus epsilon. And then we want to be able to list decode that. And for any constant epsilon, you get certainly a polynomial upper bound. Yeah, so we're going to need epsilon will also come in for classical hardness as well. So I don't know how high we can set epsilon. I think we give example in the paper, but I think you can get maybe up to 3/4 or something.
Mark, could you say something again about the issue of the normalization? So
I have a slide on that.
Oh, okay.
Yeah.
Wait for that.
So this crucial stage in the algorithm then is sort of you could call pseudo-classical. I mean, classical,
yes,
dilated to a quantum circuit.
Yes, the only quantum part of our algorithm is the ability to run classical algorithm superposition and the Fourier transform to go from the primal domain to the Fourier domain in order for us to be talking about the convolution. Yeah, but other than those two aspects of it, it's classical. It's just this decoding. I suppose in principle you could have a quantum decoding algorithm too. Really, we're just using classical stuff in superposition. And okay, well, I already spoiled it, but so we need the dual code to be list decodable. And remember from before that we needed the primal code to be this other thing called list recoverable. And it turns out that the only codes that, or maybe not the only codes, but sort of the first class of list recoverable codes that was proven to be list recoverable were these things called folded Reed-Solomon. Just think of them as Reed-Solomon, but there's a little bit of nuance there. So those were proved to be list recoverable, and just so happens that the dual of Reed-Solomon is essentially another Reed-Solomon code, which we also know is list decodable. So that's going to be our code then, is these folded Reed-Solomon codes, and that allows us to prove classical hardness and also get recoverability or list decoding in order to get our quantum algorithm to work. Okay, yeah, so that's sort of the main result. And now I did want to mention about the error terms, and then I'll talk about applications in the last several minutes. so if we are looking at the actual convolution theorem, what does the actual convolution theorem say? It says that if you take the Fourier transform of the product state, you get the convolution state, but we pick up the square root of n factor here. And n here is the size of the entire domain, which is huge. Right. First, it turns out we need our symbol space to be super polynomial, and then also we have a high number of dimensions, so it's super polynomial raised to the something. So certainly this n is huge, and so you actually what happens is if you try to naively analyze the error terms, just kind of the straightforward thing, you say like, okay, some of these x plus y's will decode, some won't. And some won't decode because in the worst case you can't decode past a half fraction of errors. So certainly there will be some chance of errors. It's it's negligible, but then you get blown up by the square root of n factor, and suddenly things aren't looking so good. So it turns out for Regev this wasn't an issue. For Regev, just the sort of the particulars of the Gaussian having these really small tails meant that the error term was actually much smaller than 1 over n. So he could actually do the most obvious thing and to bound the error terms and actually get them to be small. In our case, though, the errors, while negligible, they're basically like they're like 1 over 2 to the minus dimension, which is much bigger than 1 over n inverse, where remember, like this n inverse depends also on the size of the alphabet, which is huge. So we get this, the naive approach gets this, the error probability ends up being 100% or something. So it's, we have to do something else. And I won't really say much about it. We have to do a delicate analysis that basically uses the symmetry of the problem. So it sort of inherently relies on the fact that the oracle is random, and also that the decoding algorithms are sort of the decoding probability doesn't depend on your original code word. Right. So no matter what code word you started from, you add error, your decoding probability is the same. It only depends on the error term. And by sort of combining these two and doing a more delicate analysis, we were actually able to get the error to be small.
Especially in relation to the heuristically replacing a random model.
Right.
How do these
Yeah, I mean, so I guess at the end of the day, in order for, if you were to heuristically instantiate our algorithm with SHA, there's actually a heuristic in the correctness as well.
If it stopped working there, then you would have distinguished Shaw from random.
Right, which, I mean, SHA is clearly not random because it has small code,
Sure,
but it would be a surprise.
Yeah.
Cryptographers have been assuming that hash functions behave randomly for a long time, and for the most part, except in contrived examples, they do. So it would be surprised.
say just a little more about the
Not really. It's I will say, so we have an update for the paper that's not public yet, where we can we still have to end up using the delicate analysis, but we can make correctness hold for any oracles. We have to change the problem slightly. I don't really want to spend time on it, and there are 10 minutes left, but okay. Right. So yeah, the idea is that I guess the gist of the idea is that with a we don't necessarily need a uniformly random oracle. We can get away with k-wise independence for a sufficiently large k. That's just a product of the fact that our quantum algorithm is efficient. And so what we do is actually we change the problem so that you supply a k-wise independent function together with your solution, and then your solution is defined relative to the XOR of the oracle and your supplied k-wise independent function. And that makes your function now, the XOR function makes it k-wise independent. So you can get the classical algorithm to work. Then there's an issue with classical hardness that breaks classical hardness. So we have to do some parallel repetition. But in any case, you know, we're still going to need to basically use this delicate analysis. Yeah, I don't think I can really say more than just the point is you have to be careful with high probabilities. You can't just assume that it works. You have to actually look at the details. Okay, so now I want to talk about the applications. So the first is this one's rather simple. So how do we take this problem and actually get an NP problem that's in BQP but not BPP? So what we're going to do is we are going to define this NP relation that, so the instances are just bit strings of length n, and witnesses are vectors of symbols of length n. And what is so when is a instance witness pair valid? It's when the witness is in the code and the symbols all hashed to the x bits in the instance. Technically, this changed the problem, right? Because we were saying the problem was you know, all of the symbols hashed to say 1, but everything's symmetric because we have a random oracle here. So it's, you know, you can replace 0 with 1 and you still get a hard problem. So this becomes our NP problem here. Right. And note one thing about this NP problem is that the decision problem is easy, right? So basically with overwhelming probability over the choice of oracle, it will be the case that all X's are in the language. There will always exist these code words just by the, you know, because the code isn't too sparse and the set of code words is so large relative to 2 to the n, the size of the number of our instances, that with overwhelming probability, all instances will actually be in the language. It's just that it's hard to find, it's classically hard to find the witness. Right, so that's why I say, keep saying NP search problem, not decision. We can get classical and quantum separations for crypto primitives. So we can easily turn this into a one-way function that is classically hard to invert, but quantumly easy. What's the one-way function? Well, the domain is code words. And what do? You just hash each code word separately. Oh, and I should mention that I'm prepending these sort of the coordinate name to all of the code words, and that's just for domain separation to make sure that all of the coordinates sort of get their own random oracle. Right, so this is a one-way function. Why is it one way? Well, inverting this one-way function is exactly solving the search problem on the previous slide. Right, and now proof of quantumness. So what is a proof of quantumness? It's something where you have a classical verifier here interacting with the quantum prover, and the prover is trying to prove that they're quantum. So the completeness of the protocol says that the quantum prover actually can convince the verifier, cause the verifier to output 1. But if our prover were classical, then we want that the verifier, you know, always rejects, always outputs 0. And so what we can get is we get a simple proof of quantumness. What's the proof? You just solve this problem. You just solve our hard problem, and the fact that you solved it means you know by the assumed class or by the proven classical hardness relative to an oracle, the fact that you solve it meant you must be. There's a little bit of a subtlety here in that the model in which we can prove that our proof of quantumness is secure really requires a uniform adversaries that are independent of the oracle. And this is not necessarily the best reflection of how things are modeled in the real world. So if you were to have in the real world, if you're going to consider a non-uniform adversary, that non-uniform adversary could always have a valid proof of quantumness just hard coded in their description, and then just output that. So what in the sort of real world, if you want security against non-uniform attackers, you can't have a non-interactive proof of quantumness. You need some amount of interaction. And when you're in the Oracle setting, the correct way to model this is to basically allow your non-uniform adversaries to get advice about the Oracle. So what we show though is that there's a really trivial solution to upgrade our simple proof of quantumness into one that also works against non-uniform attackers, and that's for the verifier to just send over a random seed as the first message, and then the solutions are defined relative to that random seed. So you hash the random seed together with whatever you would have hashed with. And we prove it's actually easy. We just take some prior work as a black box, more or less, and we can show that this allows you to lift the security against uniform adversaries to the security against non-uniform. Okay, and then certifiable randomness, that's the last one I want to talk about. So what is certifiable randomness? It looks the same as a proof of quantumness, except that we actually want our verifier here to output a random string. And we want that if the verifier accepts, we want that the string is actually uniformly random. So, and what that implies in particular is that if the prover is, not using any randomness whatsoever, that the verifier will reject. Right, and so our observation is kind of, I don't know, I like this. So the observation is that if we take our proof of quantumness, and let's just be in the uniform case where it's just totally non-interactive. So what we can actually say is that if you assume the AA conjecture, that the solution that the prover gives us has to have min entropy. So in our particular protocol for solving our hard problem and getting a proof of quantumness, the way it works is that the adversary or the prover constructs a uniform superposition over all solutions and then measures it to get a single solution, which will be random. And we can essentially say that some randomness is inherent if you assume the AA conjecture. So there's no way for a prover, even if they're quantum, to actually come up with a deterministic value for the solution. And roughly the way this works, the way we use the AA conjecture is, okay, so suppose that a malicious prover had some way of generating a code word with valid coordinates, or a proof of quantumness, such that it was actually deterministic. With good probability, they always outputted the same value. Well, you can look at every single bit of the input, every single bit of the output, and every single bit of the output is just an algorithm, potentially quantum, that decides something. I don't know what it's deciding. It's not a natural language or anything, but it's a quantum algorithm that decides something. It either outputs 0 or 1. By the AA conjecture, there would be a classical algorithm that does the same thing, that outputs 0 or 1, the same 0 or 1 as the quantum algorithm. But that would then violate our classical hardness, because we could piece these for every single bit, we could piece the implied classical algorithms together to get a classical algorithm that also solved the proof of quantumness. So essentially what the AA conjecture says is that if you have a separation between classical and quantum relative to a random oracle, that your quantum algorithm is sort of inherently randomized. That's kind of the takeaway here. So what we can get is that this code word that the adversary or that the prover sends has to be randomized with some entropy, and so we can just extract from it. So Bob has a little random seed, and he just extracts some uniform random values from C. Right, and again, when you move to the non-uniform setting, you can't do this non-interactively, and so our solution is to send over a salt again. here, the prior work doesn't work generically due to the nature of these proofs of quantumness. It turns out we can't apply it, but we use sort of standard techniques in order to.
So I was wondering if you have an algorithm which uses some pseudo randomness, like a small amount of randomness. Would that also pass the test here?
Right. So yeah, I mean, to be honest, I don't know if there's like really compelling applications of proofs of quantumness, but right, what we want is actual statistical randomness to come out the other end. We want that the output of Bob is actually statistically random, not pseudo-random. And so you could, if you're pseudo-random, that would it's not statistically random anymore. So it sort of violates the definition. It should be as good as uniform randomness in any real application, but it technically wouldn't have full entropy. That answer your question?
Well, I was just trying to understand the reduction because it was going through the A conjecture, and I thought that over there you were using the fact that it's a deterministic algorithm, crucially to say that it violates the.
Right. So again, it's so A conjecture says that for decision algorithms, that any efficient quantum decision algorithm has a classical simulator, and so we take our supposed algorithm that may have outputted a deterministic code word and just look at the algorithm that outputted the first bit, look at the algorithm that outputted the second bit, and that's a decision algorithm for something. We get a bunch of classical algorithms through the A conjecture and then stitch those together to solve our problem.
Randomized algorithm would the same reasoning go through?
So classical randomized algorithm for.
So the A conjecture seems to say that there's a deterministic algorithm, right? So,
I'm not actually sure if the precise statement implies there's a deterministic one or a randomized one, but it doesn't really matter because our lower bound works for randomizing.
So at least I'm sort of guessing this is so, but although you said large alphabet, it looks like you only need fields of characteristic 2, so that the Fourier stage is actually kind of hard-wallish and not so bad, although
I mean, so the characteristic ends up being larger than 2. So the way these folded resolvents code aren't actually strictly linear, but essentially what the alphabet is, it's like ZQ to the the alphabet are it's of ZQ to the n, not n, but ZQ to the n percent n.
DQ or FQ? Can it be characteristic 2?
That's a good question. So I think if your goal is just to get list decoding and list recoverability, I think yes. The problem is that I'm not 100% sure with the Fourier transform that it behaves nicely if you're using a that's not prime letter. I'm just not 100% sure off the top of my head.
Okay. It would be helpful, like to compare what you were doing, what you're talking about to Scott's talk. It would be a little bit stiff. The direction of what he described. If it's just the characteristic 2 for each other. Reach my question.
Well, I don't think the Fourier transform is the bottleneck in implementing this. I think that it's the decoding.
It's the decoding, yeah. Yeah, so the characteristic, so I'm not 100% sure if it can be 2, but it's not big. Even though the symbol size ends up being large, the characteristic is polynomial at least. It's not huge. But yeah, I don't think the Fourier transform is the bottleneck regardless. It's probably the decoding algorithm. Running them in superposition, because it doesn't seem like it seems very insensitive to noise very sensitive to noise. rather complex.
Okay. Well, you said good question, so we'll see.
Okay, okay. So the talk's basically over. This is kind of the last slide. Just there's a natural question here of whether this is practical. Gives us any hope of improving the near-term prospects of demonstrating quantum advantage on actual hardware. And I think unfortunately the answer is no. Due exactly to this decoding problem. I don't even know if, like, even in the classical literature, I wasn't able to find in a short search sort of good classical estimates of the, like, even the exponent in the running time of the algorithm wasn't spelled out in the original paper. And then actually sort of implementing this on a quantum device coherently. I think it's certainly worse than the experiments currently being run, and how it compares to Shor's algorithm. I don't know. Maybe it's a little better, maybe it's a little worse. It's hard to say. But yeah, probably not any progress towards near term. Okay. And that's it. Thank you.
Wonderful. Thanks a lot. That was a fantastic talk. Any questions? Any further?
Could your work might say something about the hardness of doing a classical reduction for lattices, like the one Fourier gave quantum reduction?
I don't think so. Like the fact is that for our problem to be classically easy, we had to use a particular code, and we also had to use, and it's not really a norm, but we had to use like this different structure of the errors. I guess it maps to Hamming norm or something. And I think so in the lattice setting, you use random codes. And random codes we wouldn't be able to decode if we try to use them. And then I also just think that using L2 norm versus our norm results in a very different problem with very different hardness characteristics.
So your search problem has many different solutions for each problem statement.
Exactly.
And I guess under the AA conjecture, you wouldn't expect to have a problem with a unique solution.
Correct. Correct. Yes. So if the AA conjecture is true, it would say that for any NP problem, actually it doesn't even need to be NP really. For any problem with unique solution, any search problem with unique solutions, or even a polynomial number of solutions, that there wouldn't be a separation between classical and quantum hardness.
Can you say a little about what would go wrong by just like trying to make the random work output a little bigger to like narrow down the number of solutions to unique or polynomial?
Yeah, so I mean, our quantum algorithm will fail. And the reason is that, it's really the Fourier domain view of our valid symbols, right? So I won't go back to it. But so what happens when you expand the the set of possible outputs of the oracle is that spike at the Fourier coefficient of 0 is basically 1 over the number of outputs of the random oracle. So if you can potentially tolerate like log number of bits, but once you go beyond the log number of bits, your errors are just gonna be everywhere, and you won't be able to solve it. And even at a log bits, there will still be many solutions for every instance.
Sorry, I guess the other way you could do it is just tighten your code, but that would also lead to problems. I think.
Exactly, yeah.
in view of running this practically, you said the bottleneck is the fact that you have to run the decoding algorithm in quantum superposition, and this is going to be a huge circuit. You also have to do the random oracle in quantum superposition, right? The SHA-256.
Yes.
And is that not a bottleneck? Is it like?
So I don't know. This is the short answer. So there, people have actually tried to, do resource estimates for implementing SHA, and I forget I don't remember off the top of my head what the numbers were. Maybe I put it in here somewhere. Yeah, you would need hundreds of thousands of quantum gates, I think, based on the best estimates. Now, it could be that, right, the only reason we need SHA for the analysis of our quantum algorithm, but I'm going to forget that. The important place where the random oracle heuristic comes in is justifying classical hardness. And you could just make a leap of faith, and you could even imagine some like really simple non-cryptographic hash function, and just make a leap of faith that the problem remains hard even with such a hash function. And you could potentially get that aspect of the algorithm much better. You're making a bigger leap of faith in terms of the classical hardness, but even if you do that, you'll still be left with the decoding algorithm being.
So we're going to take a break for lunch to 1:30. Thanks, Mark.